Okay, so our topic for today is thermal energy. Now, if you could look with microscopic eyes, thermal energy is the kinetic and potential energy of molecular motion. The table that you're working on right now is probably at rest, so it's got no kinetic energy, but the molecules within the table have a whole bunch of kinetic energy. And if you add that all up, that's what thermal energy is. Now, if the object is hot, like a hot cup of tea, then the particles tend to be going a lot faster. They're not all going faster, but on average, they're going a lot faster than they would be in, say, a cold glass of milk. And again, they're not all going at the same speed. There's actually a distribution of speeds. You'll see that there's some particles, very few particles have zero speed, and very few particles have high speed, but you'll find a certain number at any speed. There is a most common speed where you've got the most number of particles are going that speed. But there's a distribution. They're not all going the same speed. Now, what we call temperature is a measure of the average energy per molecule. And the temperature doesn't depend on the size of the object. Now, if we put a hotter object in contact with a colder object, we know that thermal energy is going to transfer from the hotter to the colder. Here's a mechanical model that shows how that happens. Let us imagine, so all these particles are in thermal motion. They're zipping around really quickly. And let's just focus on two particles here that are at the boundary, and they're going to collide with each other. So the one on the hotter side is going a little faster, and the one on the cold side is going a little slower. Well, after the collision, there's going to have been some momentum transfer. So this was the speed of the hotter object, and this was the speed of the colder object. Oh, this is really not going well. Okay, let's switch to pen mode here. There we go. Okay, so this one was going fast before the collision. This one was going slow before the collision. After the collision, there's some momentum transfer. So this one's now going a lot faster, and this one's going more slowly. So as a result, some energy has been transferred from the hot object to the cold object. So this is now a tiny little bit cooler than it was, and this is a tiny little bit warmer than it was. Well, if you add up that effect over a whole bunch of collisions at the boundary at the interface, the net effect is that thermal energy is transferred from the hotter object to the colder object. And that's sort of laid out for you here. Faster moving particles in the hot object collide with slower moving particles in the cold. Okay, so there's been thermal energy transfer here. Always from the hot one to the cold one. Now, as a result of that thermal energy transfer, as we say, this is going to warm up. There's going to be a temperature change. Now, the amount of temperature change depends on the amount of energy that's transferred through all these collisions. It's going to vary inversely with the mass of the object, because if this is a really big, massive object, then a little bit of energy transfer here isn't going to change the temperature very much. There's another thing that is significant, and that is a property of the material, which is how readily it warms up, and that's known as the specific heat capacity. So this ratio gives us the amount of temperature change we expect. It's usually written in cross-multiplied form. Q is mc delta T, where m is in kilograms, delta T is in degrees centigrade or Kelvin, and C, this new quantity that is a property of the material called the specific heat capacity, that's in joules per kilogram degree. Now, we said that C, the specific heat in joules per kilogram degree, is the joules to warm 1 kilogram by 1 degree C. Actually, we didn't say that, but that's what the units tell us. So in a way, like if you look at water, it takes 4,000 joules to warm a kilogram a degree up by a degree centigrade. So water takes a lot more energy than either nylon or the wood. And then the metal, like steel, it only takes 450 joules to warm a kilogram up by a degree centigrade. So water is a lot harder to warm up. It takes a lot more energy to warm up a kilogram of water than it does a kilogram of steel. So let's warm up some water. Let's make a cup of coffee So a cup is about 250 grams, and we want to warm it up from 20 to 75 degrees. How much thermal energy is required? So the thermal energy Q is mc delta T. It's 250 grams, 0.25 kilograms. Water is 4186 joules to warm a kilogram by a degree centigrade. That's just on the previous page. And we're warming it up by 55 degrees C. So that's a quarter of 4,000. That's about 1,000. And then it's about 55,000. Let's work that out exactly. And there you see it. It's 57,557 joules. And the way the units work, we can just do the algebra because the degree centigrades are going to cancel and the kilograms are going to cancel. And so you're just left with joules, which is good. Now, how long will it take this water to warm up if it's in an 800 watt microwave? Well, power in watts is energy over time. So we can find the time just by dividing the energy over the power. The energy is this thermal energy. And the power is the power of the microwave. So we've got 57,557 joules of thermal energy needed to warm up the water, and we get 800 watts or joules per second out of that microwave. So that's going to take about a minute. There you go. It's about 72 seconds. That's how long it takes to warm up that cup of water. Here's another interesting calculation. The way that we determine the caloric value of foods, or one way that we can, is actually by burning them. And when we burn it, that thermal energy gets released, and we can capture that in a water blanket, in what's called a calorimeter. And the amount of temperature change in the water tells us the amount of food energy that was released. So here's a typical example. We burn some peanut butter, and it raises the temperature of the water blanket by 52.9 degrees. So this is the relationship we're going to use. I'm going to ask you to pause the video and try and solve the problem yourself. There's a couple of steps involved. One involves a ratio at the end, so it's a good problem. And then turn the video back on and watch my solution. So pause it now and give this one a try. Okay, so for the solution, we need to realize that it's the water that's increasing in temperature, so we use the mass of the water, and it was 0.45 kilograms. And we use the specific heat of water, and the temperature change of the water. Again, unit-wise, kilograms cancel, and degrees centigrade cancels. So we're just left with joules. Now then, this is the joules for an 8-gram serving, because we're told that's the amount of peanut butter that was actually in our calorimeter. So let's see how much that is. So 99,647 joules. 99,647. Pardon my dyslexia. Now that's for 8 grams. So we want to know the energy per serving. So that's 99,647 joules. Oh, that's hideous. Try that again, please. 99,647 joules per 8 grams. But of course, there's 50 grams for every serving. So that'll give us the joules in one serving. We were asked to convert it to calories. Now, a food calorie is 4,186 joules, if you remember from earlier in our unit of study. So let's see what that works out to. So we're going to take this, divide it by 8, multiply by 50. So that's the joules per serving, and then divide by 4186 to make it calories. And it's about 149 or about 150 calories. Which makes sense for a serving of peanut butter. All right, so that is thermal energy, mc delta T. Now, we're going to go back to this problem of putting a hot and cold object together. And ultimately where we're headed to the problem of body heat. So when we put two objects together, if they're isolated, then energy lost by the object can only be transferred to the cold one. So Q lost has to equal Q gained. Or another way of putting that is MC delta T lost must equal MC delta T gained. Now, in that expression, you need to be a bit careful because if you're losing thermal energy, then the temperature is going to be going down and delta T is going to be negative. So we've got to make sure to put an absolute value here for the delta T lost. Let's write that a little more neatly, please. So it's going to be MC delta T lost in absolute values equals MC delta T gain. All right, so for instance, let's just do a little thinking problem here. Bucket, okay, 1 kilogram of water. So 1 kilogram of water at 20 degrees. And then there's a kilogram of steel, same amount of steel, but this is at 110 degrees. And if I drop the steel into the water, what final temperature do they reach? Now, at equilibrium, they'll both be at the same temperature. What's it going to be? Well, here are some options. It's multiple choice. 1, 2, 3, 4, 5. I'm going to ask you, without using your calculator and without writing down, well, you can write down an equation, but we're going to ask you to try and reason it in your head so that the sorts of calculations you're doing just involve ratios and approximations, because it is multiple choice, so you just want to figure out which of these choices is closest to the answer. So pause the video and think about what the final temperature would be if we drop 1 kilogram, 110 degrees of steel into 1 kilogram, 20 degrees centigrade of water. Think about that for a moment. Okay, so now the solution to that problem, well, we imagine sort of the temperature scale here, and then at one end is the cold water, that's at 20 degrees, and then at the other end is the hot steel at 110 degrees. Now, one answer you might think is, well, the amounts are the same, it's just going to be halfway, and halfway between them would be 65 degrees, or sorry, 65 degrees. But then we remember that it's not as easy to warm up water as it is steel, so that water tends not to change very much in temperature. So we can probably reject the 65 degrees. In fact, the water is not going to change by anywhere near as much as the steel does, so it's going to be down here on this side somewhere. That enables us to reject choice C. So now we have 3 choices left, all of which satisfy the criteria that the water is not as easy to warm up as the steel. So probably we need to look at our relationship now. So this is MC, okay, on this side's the water, so I'm going to say MC delta T gained by the water equals MC delta T lost by the steel. Now, because the masses are the same, that's not a factor. But the specific heat of water is 4,000, and that's about 10 times the specific heat of steel. So because this is about 10 times bigger, we expect the temperature change of the water to be about 10 times smaller. So roughly we expect like a 1 part to 10 parts temperature change. Since C water over C steel, no, let's not write it that way. Sorry. Oops, come on, eraser, don't let me down now. There we go. So we're going to say, since this is 10 times bigger than the steel side, this must be 1/10 smaller than the temperature change of the steel. Now, it's not actually 10, it's probably closer to 9, so this should be about 1 part and 9 parts, but 10 is nice and you can do it in your head. So let's look at these final temperatures and see which one is close to a 10-to-1 ratio. So 21 degrees, well, that would be 1 degree temperature increase for the water, and then like an 89 degree temperature change for the steel. So that's a 1 part to 89. That can't be right. Then let's look at 50. If it was 50 degrees, that's a 30 degree temperature increase for the water and an 80 degree temperature drop for the steel. So that would be 30 to 80. That's an 8-to-3 ratio. That's way too small. So only 30 degrees comes anywhere near close to the ratios that we need. That's a temperature increase of 10 degrees. So the water has gone up by 10 degrees, and the steel has gone down by 80 degrees. So that's 8-to-1, and that's close to the 9-to-1 or 10-to-1 ratio that we need. So 30 is certainly the best answer there. All right, now you may say, well, why you bother doing this? Well, because it helps us build intuition about what's actually happening here. Okay? Clearly, we could calculate this, and in fact, at the top of the next page, the actual answer is worked out. So here's a Q lost equals Q gained equation, and then it's solved to give this 28 degrees, which is quite close, 28.7, which is quite close to the 30 we approximated on the previous page. So how do you set up this equation? Well, let's just do another example, because this one's already kind of been, let's see, dealt with in some length. And by doing this other one, you'll see how to set up these equations. So here we're again going to drop a piece of steel in a bucket of water. So this is 30 liters of water, and a liter of water is a kilogram, and it's at 20 degrees C. And then we're going to take a piece of steel at 175 C, and it's 0.25 kilograms. And then we're going to drop that in there, and we're going to ask, what final temperature does this reach? So Q lost by the steel is going to equal Q gained by the water. And this equation assumes that thermal energy is not lost to the environment in this process. So this really needs to be done in an insulated container for this equation to be strictly true. So this is going to be MC delta T lost by the steel equals MC delta T gained by the water. All right, so the mass of the steel is given as 0.25. We look back and see the specific heat of steel, specific heat capacity of steel is 450. Now delta T for the steel, well, it's going from 175 to T, but we have to make sure this is a positive number. So because T is smaller than 175, I'm going to do 175 minus T. That's now a positive number. On the water side, it's 30 kilograms, 4186 joules to a kilogram by a degree. The temperature change of the water, T is bigger than 20, so I do T subtract 20. Solving this equation for T will give you the common final temperature. Now, it's a fairly straightforward linear equation. All right. Now, there's going to be a complication here, and that is that phase changes, because not only, a material doesn't go on increasing in temperature more and more and more as you add more thermal energy. At a certain point, you're going to reach a phase change boundary. And for water, we know that happens at 0. So if you've got some ice and you start adding thermal energy, well, if the ice is going to start to melt into water, notice that the temperature doesn't change as that's happening. In fact, the temperature remains at 0 throughout that phase change. So there's no temperature change at all. Now that means that the thermal energy transfer relationship that we had earlier is no longer going to equal, or no longer going to have the same functional form. That just wouldn't make sense for a phase change. In fact, the amount of thermal energy for a phase change just depends on the mass and then a constant called the latent heat. Now, the latent heat depends on two things. It depends, first of all, on the material, and second of all, it depends on the phase change taking place. So for instance, if we look at water, there's a latent heat for fusion and a latent heat for vaporization. Now vaporization is going from liquid to gas, and fusion is going from solid to liquid. But the good news is that for vaporization, that latent heat can either be absorbed or released. So that one constant describes both the vaporization and also the condensation. Same thing for fusion and for solidification, or for freezing. Now the values for water are the latent heat of fusion. I think these are probably given in your notes. Is 334,000 joules to melt a kilogram of water. And then for vaporization, it's 2,256,000 joules. And clearly we're having some pen issues there, so let me pause for a second. Okay, so I think I got that fixed. So there's 2,256,000 joules to vaporize a kilogram. Now, this is called the latent heat of vaporization. And so it's helpful to have a name for the other one, right? Our MC delta T, we call that a sensible heat. So latent heat and sensible heat. Okay, so we'll do one last example in our video here. Let's imagine that you reach in and touch some steam. And that steam is going to hit your skin, and it's going to condense, and then it's going to release latent heat, which is going to give you quite a bad burn. Let's just see how much thermal energy that is. So this is condensation. So we use the latent heat of vaporization or condensation. It's 20 grams, so that's 0.02 kilograms of steam, and it's condensing, so it releases 2,256,000 joules for every kilogram of vaporized steam. So there you go, 45 kilojoules. So that's how much thermal energy is released and absorbed by the skin if the steam completely condenses. Now, steam was of course used for power because you could compress it and you could do work on it, and then you could let it condense and capture that latent heat. So it was really good for transferring energy, say from a boiler to a piston. The only problem with it, or one of the problems with it, is that if your system started to leak steam, you could get terrible burns from the steam, because if you happen to touch it and it condensed on your skin, it's going to release a lot of thermal energy. And so, steamships and things like that, the steam engineers had to be very cautious so they didn't get burned to death. So that's it for our pre-lecture video. We'll pick up at this point in class. We'll talk a bit more about sensible versus latent heat, and then we'll get back to the Q lost equals Q gained equation involving phase transformations this time. A little bit